We're about to dive into one of the biggest, most mind-bending mysteries in all of modern physics. What happens when our absolute best theories of how the universe works make time itself just vanish? All right, so here's the game plan for our little cosmic detective story. First, we're going to tackle this paradox of frozen time. Then, we'll check out a new theory that looks for clues underneath spacetime. From there, we'll uncover a hidden clock, see how it gets time moving again, and finally, we'll explore what this all means for a totally new theory of gravity.
Okay, first things first, we're diving right into the heart of the investigation. A problem so deep it kind of suggests our entire universe might be, in a way, just stuck.
I know. It sounds like something straight out of science fiction, right? But believe it or not, this is a real question that pops up when physicists try to write down the ultimate equation for reality. It's a paradox that has stumped some of the sharpest minds out there for decades. So here's where it gets really strange. Physicists have these two incredible theories: Einstein's gravity for all the big stuff and quantum mechanics for all the tiny stuff. When they try to mash them together, the math just gets weird. The equations they come up with seem to describe a universe where nothing ever changes. There's no evolution, no tick-tock of a clock. This is the problem of time, and it's a massive roadblock on the path to a theory of everything. So how in the world do we solve this? Well, there's a new model on the scene. It's called the Conformal Emergent Reality Model, or CERM for short, and it has a pretty radical idea. What if the answer isn't in spacetime, but somewhere deeper?
For the longest time, we've basically thought of spacetime as the fundamental stage that reality plays out on. But CERM says, hold on a second. It argues that spacetime isn't the base layer at all. Instead, it's an emergent property, something that arises from a more fundamental reality. Kind of like how the wetness of water emerges from a bunch of individual H2O molecules. This deeper layer is called a conformal manifold. Now, try to picture it like a blueprint for reality that only shows connections, like what can cause what, but there are no measurements on it. No inches, no seconds, no nothing. It's a universe of just pure relationships, a kind of pre-geometric reality just waiting for scale to show up. So if space-time and even time itself aren't fundamental, then where does our clock come from? Well, this leads us to the biggest clue in CERM's whole solution. The strategy here is actually really clever. See, most theories try to take quantum rules and just slap them onto space-time directly, and that's exactly where time seems to freeze. CERM does the opposite. It goes down to that deeper blueprint level we were just talking about and applies the quantum rules there before space-time even exists. It basically builds reality from the ground up, instead of trying to break it down. And this leads to the absolute core of the whole thing, a brand new kind of uncertainty principle. You've probably heard that you can't know a particle's exact position and its momentum at the same time. Well, this theory suggests a similar trade-off. On one side, you have the curvature of space, which we're calling r, and on the other, you have this new fundamental kind of time called prototime, or tau. And they are intrinsically linked. The more the universe's geometry shifts and changes, the faster this prototime ticks. They literally define each other. And get this prototime isn't just some abstract number in an equation. The theory says it's a real physical thing. It's a clock that's literally built into the fabric of the cosmos, where every tick is the universe's own shape and curvature changing. You could almost call it the universe's own heartbeat. Okay. So let's walk through how this built-in clock actually unfreezes the universe and lets things, change and evolve. So the process basically works like this. First, the theory takes those quantum rules and applies them to that fundamental, scaleless blueprint. And then, out of the dynamics of that quantum blueprint, our familiar spacetime just emerges. It's almost like a 3D image appearing from a 2D hologram, and that's the key. Time isn't an ingredient you throw in at the start. It actually grows out of the most basic rules of the universe. So, what's the big payoff here? Well, solving the problem of time isn't just some fun academic exercise. It gives us a brand new and really powerful foundation for understanding gravity itself. And honestly, the results look pretty promising. It gives us that physical clock, which solves the whole frozen universe problem. But here's the really important part. When you zoom out from the quantum level, the theory's equations become identical to Einstein's general relativity. That is a critical test. Any new theory has to match the reality we can already see. By doing all this, it carves out a consistent, logical path toward a unified theory of quantum gravity.
So the big takeaway here is that by completely rethinking where time comes from, this model might just be the missing piece of the puzzle we've all been searching for. It could be the bridge that finally connects the bizarre quantum world of tiny particles with the massive cosmic scale of gravity, pushing us one giant step closer to a true theory of everything.
And all of this leaves us with one final, absolutely fascinating question to chew on. What if the time we all experience every day is just a shadow of a much deeper reality? A reality where the ticking of the cosmic clock is nothing more than the constant, dynamic evolution of the universe's own geometry. A universe that quite literally keeps its own time.